questions about if you have an element, symbol, and the numbers, you know what they mean. The larger number is the atomic mass number, protons and neutrons, and the atomic number is simply the protons. And so appreciate what it means to be an isotope. An isotope is different forms of the same element. That means they can only have the same number of protons, but can differ in their neutrons. And if you have more than a basic number of neutrons, then you are radioactive, right? Make sure you appreciate the concept of mass defect, where when you add protons and neutrons together to make a nucleus, it's not like making a cake or a pudding, where you just stir them together and you've got the pudding. You have to do extraordinary things in nature to get those entities to all coincide together. And how does that happen exactly? Well, that happens with tremendous forces being generated to hold protons in place because they're so repulsive to one another. That difference is in mass and then ultimately energy. We call it a mass defect. So the separate pieces together compared to all of them together don't match. That's not what we see in our world. Okay, we always see conservation of mass in chemistry, but not in nuclear chemistry. And of course, once you've got the mass defect, you can convert it into energy going several ways, right? On the diploma exam, you'll only be asked to work in kilograms, not in atomic mass units, so that's a good thing. So you won't have to work to 6 decimal places, just 3 by equals mc squared. So it works pretty well. You'll see that today. Nuclear scales, for example, the atom itself, the nucleus is very tiny compared to the actual atom itself, right? So the atom's diameter is quite a bit larger than the atom. And if you think about ionizing an atom, that is taking its electron away, the energy is very humble. For hydrogen, it was just 13.6 eV. But to actually break apart neutrons and protons in a nucleus, you need millions of eV. Okay, so the electron energy is far, far, far smaller in an atom, and that's regular chemistry compared to the nuclear reactions that we've been discussing. So appreciate the difference in scale. Remember we looked at this drawing. I just appreciate that if you look at the number of nucleons, that is the atomic mass number versus the binding energy per nucleon, as atoms get larger, their binding energy, their stability becomes greater until you get to iron, and then it tends to diminish as the atom gets larger. What does that mean? That means that up to about iron, you can fuse elements together to make them more stable and release energy. But then past iron, you've got to split them apart to make them more stable to release energy. So this is what we currently do. This is what we'd like to do, right, in our future. So there's a bit of an explanation.